Hello, hello. No, don't leave. You did not click on the wrong button. You are indeed on Alex Andorra's podcast. The podcast that took the Bayesian world by storm, learning Bayesian statistics. And that Barack Obama once deemed the best podcast in the whole galaxy. Or maybe Alex said that, I don't remember. Alex made us discover new methods, new ideas, but mostly new people in the Bayesian world. But what do we really know about him? Does he even really exist? Well, to find this out, I put on my Frenchest beret, a baguette under my arm, and went undercover to try to find him. And I did find him. So today, for a special episode, I will be the one asking questions and making bad jokes with a French accent. But before letting him in, here's what I got on him so far. By day, Alex is a Bayesian modeler at PyMC Labs consultancy. By night, he does not fight crime, but he's an open source enthusiast and co-contributor to PyMC and ArviZ. Alex obviously loves statistics and loves building models and studying elections and human behavior. And when he's not working, he loves hiking, exercising, meditating, and reading nerdy books and novels. He also loves chocolate a bit too much, but he doesn't like talking about it. He does prefer eating it. This is Learning Bayesian Statistics, episode 57, recorded January the 13th, 2022.
Welcome to Learning Bayesian Statistics, a fortnightly podcast on Bayesian inference, the methods, the projects, and the people who make it possible. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country, and reach a true Bayesian state of mind by visiting learnbayesstats.com. That's learnbayesstats.com. Do you want to support the podcast and unlock exclusive Bayesian swag at the same time? Then you can visit my Patreon page at patreon.com/learnbayesstats. Starting at €3, you can get various benefits like the private MBS Slack channel, early access to special episodes, selecting questions for episodes, or even coming on the show. You'll get more details at patreon.com/learnbayesstats. Thanks a lot, folks. I'm very grateful for any support you can bring me.
Let me show you how to be a good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. What's a Bayesian? It's someone who cares about evidence and doesn't jump to assumptions based on intuitions and prejudice. A Bayesian makes predictions on the best available info and adjusts the probability, cause every belief is provisional. And when I kick a flow, mostly I'm watching eyes widen, maybe cause my likeness lowers expectations of tight rhyming. How would I know unless I'm rhyming in front of a bunch of blind men dropping placebo-controlled science like I'm Richard Feynman?
Welcome to Struggling with Bayesian Statistics. Thank you for accepting my invitation, even though we're on a competing podcast. So you're here because you are interested in statistical modeling. You're pretty famous with your podcast in the world of statistical modeling, but you didn't start on that path, did you? You've got quite an interesting background.
Yeah.
Can you tell us about it?
Yeah, interesting, I don't know, but sinuous, that's for sure. And yeah, thanks a lot for having me on your podcast, Rémi. I learned a lot. I heard a lot about learning Bayesian statistics, and I'm very happy to be a guest now. I'm honored, should I say. So yeah, thanks a lot for having me. And I'm flattered that you think my background is interesting. So what's my origin story, let's say? Yeah, I absolutely didn't start by nerdy topics and so on. I come from a family where computers are basically the enemy. No, so,
oh, wow.
I'm exaggerating. If my mother and my father are listening to that and understanding, they won't be happy. No, it's not the enemy, but like, we're not particularly technology savvy in the family. So I didn't start coding at 12, like some guests on these very podcasts.
Like 90% of the guests.
So yeah, I started coding actually super late. I was 27 when I first heard about Python and what we could do. I first did business school in France, traveled a bit thanks to that, went a bit to the US and lived in Germany for a while to do political science. And actually, while in Germany, I had the opportunity to write a book on the US. So that was a geopolitics of the US. And the book is called like that, like very originally. And so while writing that book, it was during the summer of 2016. Of course, there is no famous presidential campaign in the US took place during that time. And while writing that book, I discovered all the different models that they have in the US, especially 538. And the nerd in me was awake. I was like, oh my God, this is awesome. This at least helps people to say less crap, at least have more data-driven narratives, even though those narratives can still be crap. At least it's a bit more data-driven and as objective as we can get. And that's what I want. And at the time, I also was missing math and stats, which I studied quite a lot before business school. And then in business school, you don't do that anymore. So that was answering a lot of my questions at the time. And so I was like, okay, I have to do that in France now. And so I started doing that in 2017. A very, very basic model.
So that was 4 years ago. Yeah. 5 years ago.
Almost 5 years ago. Yeah. And I started like diving into Python, building the website on Python to display the graphs that I was building with the model. Very, very basic model. Now that I see it's I have some empathy for that model, but it's a very baby model. But I like it nonetheless.
Now you'll need to release on GitHub, and we'll put the link in the show notes.
yeah, exactly. And so that's how it all started. And I started diving very deep into Bayesian stats thanks to that model. And then after that, I started entering open source and so on. But I think you have some questions about that, so I'll let you talk now.
Yeah. How exactly did you stumble upon Bayesian statistics while doing this? Because I don't think that 538 is explicitly Bayesian. I'm actually not even sure the model's Bayesian. And what did you find? What was the first paper or book or blog article you saw that mentioned using Bayesian statistics for that? So
I actually remember that, and I hate reading academic papers. So I highly doubt that I found that in an academic paper. But I did read Drew Linzer's paper, I think from 2013, about the dynamic Bayesian model to forecast the election. But at the time, I was such a beginner that I didn't understand anything in that model.
What is this?
Yeah. I just understood a bit of the structure and was like, okay, I think that's what I need to do. That's the model.
I think that's pretty cool. Yeah.
But I was like, but I cannot do that neither programmatically nor statistically. I don't understand that. So I'm going to go with something much simpler. I think that's where I started hearing back about Bayesian stats, because I already knew about Bayesian stats in my undergrad. But 538, it's weird. Nate Silver is always advocating Bayesian stats, but we don't know whether the model is actually really Bayesian or not. And, but I did hear a bit through that, and just it was very natural. I remember that only that one main framework of statistics allowed you to estimate uncertainty. And I understood very fast that I needed to estimate uncertainty, that it was quite dumb to just have point estimates, because uncertainty is super high, especially in French elections where you have a lot of candidates. And so they can be very close. And here it's really the uncertainty that counts.
Yeah, we'll definitely talk more about political science and what Bayesian statistics have to do with it during this episode.
Yeah.
I see that I'm going to start with that, and then we'll get to what you're currently doing. It's part of it. I saw that you released a course that's called Intuitive Bayesian Statistics with Thomas Vicky and Ravin Kumar. And it's pretty interesting because you learned Bayesian statistics, you don't have a quantitative background like most people do, even though they're not statisticians, most people come from biology, from physics, from many other quantitative fields, and you don't. So it's very interesting that you wrote that class. And I guess my question is, what was the most difficult thing for you when you started learning Bayesian statistics?
Yes.
And what got you unstuck? What was the most difficult, and how did you get unstuck, basically?
Yeah. So there are I think there are two things, one very specific and one more general. I'll start with the specific. Well, like I remember the most confusing concept for me was forward sampling. Like it took so long for me to understand forward sampling, so prior predictive distribution and posterior predictive distributions, because Bayes' theorem is super easy to understand. The intuition is super fast. Interpreting the results and the HDI, the intervals and so on, it's super easy. But then I was like, what's that posterior predictive stuff? Like I don't understand the difference with the posterior and prior predictive. I was like, what's that? And it took me quite a long time and several exposures to different resources. The first book I read Osvaldo Martin's book, who introduced me to all that. Which
is very accessible.
Yeah, exactly. Really, really good book. And I had a first understanding of that, but this was still fuzzy. And then I really understood that concept, I think, through Richard McElrath's book, Statistical Rethinking. I don't think there is a causal link here. Like maybe if I had read the two books in different orders, I would have had the eureka moment with Osvaldo's book. Because something I often say is that usually when you start learning something, especially Bayesian stats, your favorite book is going to be the second one you read.
Yeah.
Not the first one.
The second one.
Because the first one you won't understand a lot.
My first one was BDA3, so I can tell you I did not understand a single thing. I was like, what is that? It's like, but I kind of like it. Kind of sounds cool, so I'm going to pick up another book. And
listeners, don't do that at home. Like, don't do start with BDA3 alone in your room.
I'm a professional. I know what I'm doing. Don't do this.
Yeah, exactly. Don't do that at home.
We did it for you, don't.
Yeah.
It's an excellent book, though, and you should get it once you're familiar with Bayesian statistics because it's a great reference. But don't start with this.
Yeah.
But it's mind-boggling that the thing that you found difficult was forward sampling and not sampling from the posterior distribution. I mean,
MCMC and so on, you mean? Yeah. I wasn't bothered by that. I was like, okay, that stuff I know it's very difficult, but I trust the guys who are much smarter and better than me that this is doing a good job. I mean, like Betancourt, Gelman, the PyMC guys and so on, they say that works. That's that, and you should trust that unless there are some warnings and so on. Okay, I'm going to trust them.
And you don't trust them with forward sampling.
No, I do. I just don't understand. I was like, what's that?
That's really funny.
Yeah.
And now do you understand it?
Yeah. Now I love that. And I love explaining that to beginners.
Okay, so explain, like, give us the elevator pitch of why you should look at forward sampling. Because, I mean, posterior predictive, you can explain in 2 sentences and then, maybe why you would do that with prior predictive. I'm
going to tell you how I understood that, and that's going to lead me to the general point I wanted to make about what was the hardest for me. So how I ended up understanding that is the function to do posterior predictive sampling in PyMC 3 was messy in the sense that it was not a first-class citizen. It was not originally in PyMC 3. So often you would have shape issues when sampling posterior predictive sampling.
Okay. Yeah, that's true.
That was actually a good thing because often in my model, pm.sample posterior predictive would break. And so I would have to implement posterior predictive sampling on my own. And then I understood how to do that because I had to do that on my own. And that's where...
With SciPy? Is that how you do it?
You can use SciPy or NumPy or PyMC. You just sample from the distributions that are in the model. And once you understand that, it's basically you have to rebuild the model, but instead of having distributions that you want to infer, you have those distributions. Now you sample from them. It's just that. And that's how I understood forward sampling. I was like, okay, that's why it's forward. And the inference is backwards because we go from data to parameters, whereas here in forward sampling, we go from parameters to data. That's simple. And that's how I understood it. Just because there was this good function in PyMC, but that often broke. By the way, in PyMC 4 now, it's much more robust. So most people won't have to do that, I guess. But yeah, that's how I understood it. And more generally, the pain point was just start coding. Don't try and understand everything. Just start coding your model and do it, and you will understand why I'm doing it. And that's also the spirit I got from starting working in open source. So that's the best decision I took in my life, was to port statistical rethinking from R to PyMC3 and starting contributing to the PyMC resources repo. And there I had the incredible, generous help from Osvaldo Martin and Ravin Kumar, who helped me a lot going through the exercises, porting that to PyMC, porting the course. And I made a ton of mistakes there. They helped me. I fixed them. And that's really how I jump-started my learning when I started open source, like contributing to open source that way.
I remember you were everywhere on the PyMC discourse at the time. It's like whenever someone asked a question, Alex Andorra was here to answer your question.
Exactly. Yeah. That was also a way I learned, is that I went on the discourse, and at first it was to just understand, because Junpeng Lao is like an amazing wizard. So he had like all these solutions that I was reading and was like, okay, I didn't understand that. Or I was like, oh, that's awesome. How did you get that idea? And then at one point I was like, oh, okay, I can answer that question. I'm going to try and answer that. And maybe I'm wrong, and Junpeng will correct me, and now I'm less wrong. So yeah, that was also a big part.
But
and that's basically the general point. Was, I think the most difficult was starting doing it and daring doing it, because you know you're not good, you know you're a beginner, and you're afraid of that. But the solution to that is actually to just be super open about that and just go contribute to open source, contribute to the discourse, and make mistakes. And actually the community is so welcoming and safe.
In Bayesian stats, it is still.
Yeah, that really jumpstarts your learning. And Eric Ma, actually, who is a fellow PyMC developer and friend, and also came on this podcast, has a very good image for that, because he uses that to learn a lot of things. He says that he always has an open garage when he learns something. And so he always blogs about the stuff he's learning, even though he's still like a very beginner in that, because that's how best he learns, basically.
Yeah. And you can, I mean, now we have better than blogs, we have Twitter. So you can just, you can just do something and publish it immediately and then get feedback. And I guess that you're right. The secret is to get some really terrible code out there and realize that no one, that you're still alive 2 days later, and that no one will judge you for it. So
yeah. And the community is really great. So most of the time you won't have any shit thrown at you. It's really an amazing community. So take advantage of it.
So you'd say the secret is code and publish your code.
Yeah. Like do it,
Just do it.
Yeah.
Like someone said.
Yeah, exactly.
And so I guess that your course is taking that approach code first.
Yeah, definitely. The course we have with Ravin and Thomas. So first, it's amazing to develop, because I guess you know that like teaching is always a huge challenge, and that's how you learn even more, I'd say.
Yeah.
And the vision we have for the course with the guys is always try to start with the application and then explain what happened. And the way I think about that is like an Agatha Christie novel. So when you read an Agatha Christie novel, you have all these details and so on. And at the end, you understand who the murderer is because she helps you do that. But when you get there, very often you're like, oh my God.
I should have seen,
exactly.
I should have known.
I could have guessed that from page 10. You go back there and you see, oh my God, it's already all in there. How did she do that? It's amazing. And when you reread the novel, you're like, oh, there is all these clues.
It's obvious.
Yeah.
They're everywhere.
It's obvious and it's mind-blowing. And that's the approach we want to have with the course, is to help you go through Bayesian examples and models. And then you'll see, okay, let's look at that concept and so on. But look at that. You already know that concept. You already used it just now, instead of going the other way around, which is like, here is the concept and now let's apply it.
That's a very good pitch, is learning intuitive Bayesian statistics as good as an Agatha Christie novel.
If we can get there, I'd be super happy if we can get that. Like, that'd be awesome.
Okay, so it's cool. So that's one of the many things that you're doing. What do you do today, like, with your days for a living, and how is it related to Bayesian statistics?
Oh, yeah. So it's very much related to Bayesian statistics. because I wanted that. So for quite a few months and years, I've really tried to have a work where I only do Bayesian stats, or at least only do statistical modeling. That wasn't always easy. That was sinuous, like my graduate studies, but I did get there. And today, so I founded with Thomas and Ravin and Luciano Paz and Adrian Zabelt at the very beginning. We started PyMC Labs, so which is a Bayesian modeling consulting company based on PyMC. Of course, we are all PyMC developers in the company, and yeah, we help our clients with their modeling troubles and questions, and that's very fun because they often come with very challenging problems. Sometimes it's really in your ballpark and you're like, oh, okay, I know that's my specialty. I know how to do that. But also often it's, okay, I didn't even know Bayesian stats were used in that industry, but that's super interesting. Let's get into that. The challenge is really interesting. So let's do that. And yeah, basically, so my work is working with Bayesian models every day, learning a lot, because that's the beauty of statistical modeling, is that every case is different and you have to always adapt and learn. And also contributing to open source, which is for all of us at PyMC Labs is super important. And what we're trying to do is to integrate really the fact of contributing to open source with our work. And that's really something we are very passionate about. And I'm super happy about that, because recently when such situation happened where we started developing a helper function for a client on how to choose priors under constraints. So for instance, if you have a beta distribution, it's super hard to find the parameters, right? You have to do manual trial and errors.
Because experts are never going to tell you should take alpha equals 0.732 and beta equals to 5.7.
Yeah,
that's not how humans work.
Yeah, and so the beta is amazing because it's very versatile, but precisely because of that, it's very hard to choose the parameters. And so for that client, we developed a function where you could say, okay, I want 95% of the mass, for instance, between 0.1 and 0.4, and now give me the parameters that correspond to that. And so we start. Which is how humans think, right? Yeah, exactly.
In terms of priors. Yeah, so that's...
And that makes also prior elicitation from experts much easier, because you can just ask them, okay, what do you think is a credible conversion rate? And then that's okay. You don't need to tell me the parameters of the beta distribution, which you don't even know. So we did that first version. Then I developed that more with Luciano for a workshop, because we also teach workshop with PyMC Labs in companies. And that's always also super interesting, because while teaching, I learn a lot. And then after that, we were like, okay, that function is super helpful. Let's put it in PyMC. And then I could work on that. That was a much longer PR than I expected.
Yeah, it always is.
Yeah, oh my God. No, that's why I was like, okay, I think in two commits, it's done. And then after 60 commits, it still wasn't
famous
done.
Last words.
Yeah, oh my God. And then I was at 60 commits and was like, oh my God, it's still not merged. What have I done? But now it's merged. And so in the coming PyMC 4 beta 2, you're gonna have access to this pm.find constraint prior function. And yeah, so basically that was an example to tell you that, yeah, we also try to do that as much as possible with PyMC Labs. And when we can do that, it feels really good. I was super happy to work on that and have that developed with the clients. Also, that's super awesome to also have clients who have open source who like open source and are there to contribute back.
That's cool. I'm sure that people, it's a very useful feature. It's interesting that you get actually problems that people are actually dealing with on the battlefield. So it's not just academic problems. You can bring them back to the library. And I think that's very interesting. And that's a very useful feature.
Yeah.
So, working for this consultancy for PyMC Labs, you are interacting, I guess, with many different companies. And I guess there are different levels of adoption of Bayesian statistics. And so I think you must have an opinion. I mean, I have an opinion about that, but you must have a better posterior.
I have a very good
posterior distribution on this, which is, what do you think would help to get a wider adoption of Bayesian method? Is that possible? Is that desirable? And what would help today? Like, what is the thing that people could do to make it easier to transition to Bayesian methods?
Yeah.
I know it's a heavy question.
Yeah, it's such a wide question. Such a wide question. No, so to start with a very specific thing, I think most of the time, the issue people have, including me when you're modeling, is basically the workflow and not losing sight of why and what you're modeling. Because when you start digging deep into the model and how to choose the priors and why it's not converging and why is there these 10 divergences still, it's just like, I still have that warning about 25% effective sample size and so on. So you can get caught in like very deep stuff and losing sight of what you're doing and why you're doing it. And then you lose in your head, you lose the fact that, okay, I'm there in the workflow. What should I do next? So that kind of almost automated, not thinking, but process, that's usually very hard. And that's what I see in companies and also from beginners, is that they get overwhelmed by the quantity of things that have to be learned. Yes, but I mean, look at the alternative. It's not like classic stats don't require any learning. But so you have to learn and spend time on that. But the automation can be improved.
Yes. Okay. So you think there's a part that's educational and you think there's a part that's like more like tooling that's missing?
Yeah, exactly.
Okay. So what would that be? What would that look like?
Yeah.
If someone's listening today and wants to write terrible code like we suggested earlier.
Yeah. So the education part, I mean, it's way longer and so on, but of course we need more of that at university. Basically, we need more Bayesian stats course at university. That's what Aubrey Clayton, for instance, talked about in episode 51. I think David Spiegelhalter also talked about that in episode 50.
About that, yeah.
So of course there is that. I'm never going to say we don't need that. And on the tool part, I think what Aki Vettari, Paul Bertner, and people at Alto also are working on, which is an automated software workflow, basically, is very interesting. So the idea is you start running a model on count data, for instance, but you're using a normal likelihood. Then the software would tell you, are you sure you want to do that? Have you thought about the Bernoulli distribution, for instance? Because that's more appropriate most of the time, so like having a small, that small statistician instead of having it like close to you, because there is not enough Bayesian statisticians. You have it on your computer,
I'm laughing because we've all done that.
Yeah, exactly. Yeah, that's the point.
I mean, even knowingly sometimes, like, okay, don't bother me with that software. I know I'm a terrible modeler.
Yeah, exactly. And so like, that'd be awesome because often people are overwhelmed by, what is the good prior? And I always answer, there is no good prior. There is no one best prior. Like, try something and then you'll see. Most of the time, you end up choosing the same thing because some distributions are awesome. So you use them most of the time, but sometimes you will use something else. So there is no one best prior, but people want that. And so, having a more guided workflow and automatically guided workflow, I think would be incredibly valuable. So that the second thing is making forward sampling checks much easier. So like prior predictive checks and posterior predictive checks.
But that's going to be the case in PyMC version 4, no?
Don't worry, it's
Isn't
PyMC.
That something
it's called PyMC now. And just the major, now it's normal. The name of the package is PyMC and the version number is just 4.0. Blah, blah, blah. Okay.
I'm sorry, I got lost.
Yeah, I know.
Just to say, that's going to be the case.
Much easier.
In PyMC when the version 4 was released.
Yeah, the version 4 is actually released. You can already do conda install PyMC, and that will get you on your computer PyMC 4.0.B1. So beta 1.
B1, okay, yeah.
At the time of this recording. And beta 2 is really in the works, almost done. And so you can already run PyMC 4 on your machine. And I already use PyMC for some clients at PyMC Labs. So you can already use that. So yeah, that's much easier. What I was talking about is visualization, because forward sampling, you need most often like customized plots, right, for your model to really understand that. And so you will never be able to have a library with all the possible plots. But a good thing, I think, would be kind of a software-assisted Bayesian workflow for the model, but then for the plots. So like, oh, I see you have multinomial data and it's a time series. Usually these kind of plots are useful. And if you also want to check the robustness of your inference, these kind of plots are useful. Just that,
Okay.
And
so that's, that'd be great. That'd be definitely great. So that would be more for like beginners / intermediate users. Can you identify actually, I like to ask that to people who actually, like see a lot of companies using Bayesian methods, because you always feel alone when you're Bayesian in the industry. Usually you feel like you're the only one working on this thing, but you're not.
Yeah, you're not.
Alex is here to tell you that you're not alone.
Don't worry. You can call me anytime you feel lonely.
And so do you think there's tooling that's missing in the open source world for like more advanced users, like stuff that companies who contact you need but doesn't exist?
So for advanced users, you mean?
Yeah.
Well, yeah, I think there is a lot of things missing for advanced users because by definition, they like, I don't know if they like, but they often do their stuff on their own. So what I see is mostly missing is things helping you with this. So you are that very, very well. I don't know that as well as you do. So all this SRA, graph computation, graph manipulation, and tensor stuff for me sometimes still is very weird. And so to me, having guidance on that, I don't really know in which form would be super helpful.
Is that a subtle way to tell us that we should write documentation on these things?
I'm not sure it was that subtle. But yeah, thank you for the compliment.
Very subtle. I guess the SRA team will listen to this podcast and take notes. But I guess maybe more. There is documentation, to be fair, and it's quite. It was enough for me. But maybe more, sort of a general overview of how these things work and actually why you need something like Apple, the new PPL, and what it does that you couldn't do before.
Yeah, exactly. Like, what is it? Why would you need that? And when does it work best? Basically, that would be something I'd need. Because
that's what PyMC is based on now.
Exactly.
And that's why forward sampling is faster. It's because it's based on this. And
exactly.
Thanks to Brandon's work.
Yeah. And that's where like I should clearly give a shout out to all the people mostly involved in that. So Brandon Willard, who had like all that vision like already 1.5 years ago, and also Ricardo Vieira, who spends so much time on SRA, Apple, PyMC. So I was going to say I need to invite him on the podcast, but you need to invite him on this podcast.
I will need on this podcast.
I don't know what you're doing, man. He should have been there before me.
Apprendre les statistiques bayésiennes.
In French, yeah. So, Ricardo definitely need to come on the podcast and tell us about all that. Michel Ostege also, who was already on the podcast and works a lot on all of that. So thanks to all those folks. That's thanks to us that we have all that. And so all that stuff
and developing tooling for more advanced users.
Yeah. So how does it fit together and so on? And also basically a tutorial about how to write a custom operation in SRA that you use in your PyMC model.
Alex can see that I'm taking notes while I'm asking questions.
I think the note says, don't ever invite Alex again on the podcast.
Okay. So now let's talk about, you started with political science. You did political science for a while. You went to Bayesian Statistics thanks to that. And now for a while, you kind of never stopped.
Yeah.
You've had a project that's been going on for a while that you're going to talk to us about now. It's called Postposition, which is a very good name, by the way. It's pretty good. I'm sure you're really proud of it.
Yeah. I like puns, of course. I like that.
That one's pretty good. I think it's I think it's pretty good. And so for how long have you been doing that? Why did you start? How many, was it just you? Was it other people? I mean, just tell us all about it.
Yeah, when and why I started, I talked about that already.
Yes.
So it was in 2017. And
so that's how you discovered the Bayesian statistics was actually at the same time.
Yeah. That's because of that I went back into Bayesian stats and that I went into programming for the first time in my life. And I also, for the first time in my life, really enjoying statistics, because I was like, oh, that's awesome. The computer is doing all the computation. So the things that I don't like and that also humans are not that good at, and computers are much better at. And I can just draw samples from the distributions and have that as the plot in front of me. That's magic. So really I started doing that just to learn. And I saw that the small model that I had in 2017 got some traction, not big, but some traction. And so I was like, so that's good. What I thought was needed in France has at least a small audience. And I think it should be there in the landscape. The problem I had, and I still have a bit, but less now, is that it doesn't bring you any money. So it's a hugely time-consuming activity, because political science and electoral forecasting is super hard and takes a lot of time, but nobody is ready to pay for that. And you also take a lot of crap on Twitter. Like, the community is really not welcoming.
This one is not very welcoming.
As the Bayesian stat is. So, at one point I was even considering just letting it go after the 2019 European elections, where I had a more interesting model, more complex Bayesian model. I open sourced everything and so on. And there I was like, I'm tired of all those people criticizing the model without even looking at it, or without even taking the time to understand what a model is, and just being like, oh yeah, but all models are wrong. So I guess we should just say that whatever I think is true is as true as whatever model says, So I was like, I'm tired of that shit, and I don't need people like that in my life. So I should probably quit that stuff.
But you did not.
Yeah, I did for a while. But it's like the mafia is it in Scarface? I don't remember. When I thought I was out, they pulled me back in.
They pulled me back in, yeah.
And so I went back to that because, so first, you helped me come back to that, because you were super motivated and so on. And so that helped me get very motivated. So thanks for that. And also the statistical challenge is interesting, I have to say. These models are complicated, and that's why it's very interesting, because they are never perfect. They are never finished. You can always learn something new from that. And I started having the same spirit as I had at the beginning, which was, okay, it's my geek nerd sandbox where I get to test some new ideas for models that maybe I will end up using for clients for PyMC Labs. That's also PyMC Labs helped me get back into that, because then it was less of an opportunity cost. It was more that's a training. That's kind of fundamental research, if you want. It's you try stuff out. Often it doesn't pan out, but sometimes it will, and then it's awesome.
And then translates to everything else. Yeah.
Yeah. And surely the model we worked on for the coming 2022 elections was really that. I really wanted to, so I had that vision of the model since 2017 of a dynamic Bayesian model that I could never do because I wasn't enough of a good statistician. But now I can do that. And we have all these Gaussian processes to model the timeline of the election. And these Gaussian processes are hierarchically related between elections. And so you have one GP per party per election, and each of these GP is actively regularized by another GP for each party. And it's crazy, right? I never thought I would write such a model. And that helped me understand a lot. Okay, how do GP work? What's important for a GP? And spoiler alert, priors are super important.
Priors.
Yeah.
I want to state for the record that I was against the GPs until I realized there's a link with Gaussian processes. with stochastic processes.
Yeah. Once you realize, okay, there is a bridge there, and Gaussian processes are actually like a generalization of, what is it, Brownian motion or Brownian bridge.
With the right kernels, it's actually equivalent to random walk. So
yeah, exactly.
Yeah, and a random bridge is one example.
Yeah.
But yes, of the things you can model. But in some cases, it's actually equivalent to modeling a stochastic process, which makes a lot of sense when you're talking about opinion polls. So yeah, so that's how I got.
Yeah.
And that's how you convinced me.
Yeah. For the record, so yeah, I love GPs because they are magic and they are like beautiful. And even the math is beautiful.
Oh, wow.
But also it was grounded in domain knowledge in the sense that the classical way to do that kind of dynamic Bayesian models, especially with the Linzer paper, for instance, who was quite seminal in that sense, is using random walks and multivariate random walks.
Mm-hmm.
But I don't think that public opinion is a real random walk, in the sense that it's less dispersed than a random walk. Public opinion takes more time, and there is momentum in public opinion. Mm-hmm. And so if you want, it's a random walk, but with a wider mm-hmm. innovation. Like the innovation is slower. It's kind of an IR process with a bigger, I don't know, step size. I don't know what the term is. I never use AR process, but you know what I mean. But you don't really know what the step size is. So that's where the GP is very helpful, because it just determines the step size for you. And you can really see that public opinion doesn't vary that much, actually. It does vary, but it takes time. It takes time, weeks. Yeah. It doesn't take days.
Yeah.
And that's why the GPs are interesting here.
Okay. And so a more general question now. I mean, you see with journalists love elections because they have many things to say about opinion polls all the time. And if you had to explain to a journalist what statisticians can teach them and can do for them, what would that be?
That's a very hard question.
We'll have a harder one after this.
Perfect. Yeah. Easy questions are boring anyway. So perfect. Yeah. I pondered that question for years.
That's why I'm asking.
And
I know.
I don't know yet. I think the intuitive Bayesian course is actually helping me do that, because I have a bias. Towards technical explanations, because I'm a nerd and I love learning about the details of, why is the GP important here? Why are hierarchical models amazing, especially for electoral forecasting? And what does it mean to pull information across parties and across time and so on? But I think most people don't care about that. And so I should not talk about that when I talk with non-data people. So I think what's most interesting for journalists from these kind of models are the actionable part. So what can we say from the polls that we have seen right now? Can we actually say that this candidate is the favorite? What does it mean to be the favorite? How far ahead is he or is she? Is that latest candidate who just declared himself really a serious contender to the second round? Can you say that just after one poll and just educate people, which is something you do very well on our Twitter account on Postposition, which is but we just had one poll about that. And remember all the uncertainties there are in polls, because not all people contacted answer. Then not all the people who answered are going to vote. Then all the people who are going to vote are not certain of their choice. And after all that, all the people who say they are going to vote, maybe they are not going to vote. So the uncertainties are huge. And that's where it's another part that's very important. It's basically counterfactuals.
Yeah.
And so using plots, as you're doing with these animated dot plots on the Twitter account, which give you the counterfactuals of, let's consider that scenario. What would happen then? What would it take for that scenario to happen? And that's also where Bayesian stats are super interesting, because this is just counting. And so you just plot the dots, and each dot is a scenario. And once you have all the dots, you just count how many dots are in each bucket. And the more dots, the more probable the scenario. Yeah, that's what I think is the most important. I'm curious about what you think on that.
Like, you have to remember what it took you to get where you are today in terms of learning. I mean, it's maybe easier think about yourself before you did political science and back in 2017, all the mental steps you had to climb to get to where you are in your understanding today. And I think that you need to make people, and I mean, it's difficult. I mean, look at the model that you came up with. It's even for someone who's a seasoned Bayesian modeler, this is quite something to, it is a big model to digest. And
it was a simple PR. Just
it was a very simple
120 commits and 14 files. So it was not that big.
You can look at the PR and learn what not to do when you submit a PR.
Yeah. That was a very bad PR. You cannot say
here's 20,000 lines of code. Please review.
You cannot say from that PR that I am actually an open source developer. You cannot say that.
You can, because the code is clean. So, but no, you have to remember that you didn't get there from day one, and you have to take people's hands, I guess. Take people's hand and be like, here is why we're doing this and why we're doing that. And so indeed, we're pulling results from different polls, but there are uncertainties per poll already. So let's just explore this. And once you've understood this, let's go back and put different polls together and explain why this is a good thing, etc., etc.
Yeah. I didn't have the same objectives when I started learning that also. That's because, as I was saying, I have a technical bias, which is like, I was actually very interested in how you get there. Like, how can these methods work? Like, kind of an epistemological perspective, if you want. But how can we do that? And how does that work? How do you do that? I want to be able to do that and not just understand. And so understand the principles behind that and the statistics also. And that's how I transitioned actually from political science to statistics, because the statistics is the method and you apply that method to different fields. And so I'm more interested in the method than in the field, actually. I like to apply the methods. So that was my perspective. But I don't think most people have that perspective, at least for electoral forecasting. So you have to relate that really to the field and tell them, okay, that's what we can tell about that topic. Not about the stats stuff that I love, but they don't.
I'm going to take the example of the COVID, all the COVID modeling and stuff that happened. What was very popular in the end was just simple charts. It was just showing people information and summarizing information. The best summary of information was the website or the Twitter account that became the most popular. And I think that this is what people mostly expect, but you have the tools to make very complicated stuff actually look very easy, right? Because what is the main thing that you're doing? So French elections are coming, if people didn't know that. And the French presidential elections are coming in 2022, which is this year, actually. I just realized that. And French elections are quite complicated compared to American elections. I mean, I guess this is arguable, you're the political scientist, but talk to us about the political landscape in France, actually, and the elections, and why. Do you think it's as difficult to model as the US elections, or more difficult to model than the US elections? And what are the main differences? What makes it more difficult? What makes it easier?
Yeah. So what makes things more difficult in the US is the electoral college. The popular vote is super, super easy to forecast, basically. But the electoral college makes things more complicated. But in France, the main difficulty is that the parties are not the same historically. So we don't have like two parties which are the same since the beginning of the 20th century. They change names. Like, we also have to say that, like they don't really, it's rare that a party like really comes out of nowhere. It takes time and so on for parties to adapt and become new, if you want. But you have different forces that you can rate on a spectrum, from being from the far left to the far right and going through the right, center, left. The Greens also, who are more, let's say, a bit more to the left of the political spectrum. Traditionally in France, it's not the same in all countries, but in France it's like that. And so that changes with time. So when you do modeling on that, you have to make choices and say, okay, that party is closer to the far left. So I'm going to consider it's in the same family as these other parties, like the Communist Party and so on. But the Communist Party doesn't exist anymore, like isn't really strong anymore as it was in the 70s and 80s. So what do I do? Like, which party is now the left-wing party, the far left-wing party? These are the, I'd say, complicated decisions, but it's not that complicated. It's, if you want to think about that in a statistical way, it's, let's say that you have families of parties, and in the far left, you have distribution of party, and each election, a party is randomly drawn from that distribution, but that distribution is common to all the far left parties. So they are similar in their ideas, although the people change and so on, but it's not that big of an effect. I know it's not very popular to say that because like most of the people in campaign coverage are like, oh yeah, like people are very important, basically. The candidate makes everything and so on. I don't really think that's true. If you look at it historically, it's not like the candidate is not that important. It's part of the solution of the process, but it's not the main process or the only one, I'd say. So you can put parties in some buckets, but this here is particularly interesting because
why?
Because the left party, the traditional left party now in France is like almost non-existent. Yeah. And so that means that the left is like...
And by inexistent, we mean what, 3%?
Yeah,
intentions?
3 to 5%.
Yeah. In the polls, yeah.
And that means that you have all these different candidates on the left and also the far left candidate who are like, okay, what do we do? Like, it's really game theory. It's super interesting.
It is like, applied game theory.
Like clearly in our system, the optimal decision is to have one common candidate and go there with one common candidate. That's really how you can maximize your chance in our system. But they don't want to be the first one to withdraw from the race because then they lose any bargaining power in a potential future coalition. So nobody is withdrawing from the race. And by doing that, they divide the vote and they are basically one by one inexistent, except for the most important one, who is Jean-Luc Mélenchon. So on the far left in our model. But even then, like Mélenchon could get more votes if there was like just one candidate on the left. But they don't do that. And that's interesting to witness. But for the modeler, it's hard because like, what do we do? Although I think when you have candidates around 3%, it's not that important anymore from a modeling perspective. The most important is Mélenchon. And then on the far right, for the first time in French history, we have two candidates on the far right. And of course, here, the problem is the same. And on the far left, it's not optimal for the far right to do that.
And they're scoring about the same.
Yeah. It's like it's the Condorcet problem. Like Condorcet, had seen that already, centuries before us, that in our system, if you divide the votes, you can end up with candidates elected, which are not the choice of the majority, but it's because the majority choice were split up between different candidates. And it's exactly what's happening. And the far right, it's exactly that. Like if you combine their two votes, it's about 30% right now. Yeah. But each of them is like around 15%. But that's interesting for the modeler because then we need to model these two candidates. These 15% is huge. So you cannot ignore them. And then the question is, what do we do with the second far right candidate who is like completely new? And here it's super interesting because your forecast will rely a lot on the prior because you have polls. So the prior will be updated with polls, but you only have 3 months of polls in the election. So it's not that much. And then your prediction for that candidate almost only rely on the prior, and the uncertainty should be much higher than for other candidates. Mm-hmm. But thankfully, our model can draw on the history of past elections and the other parties and how they behave. And that should help to predict that. But that's still a huge statistical challenge. And I want to point out that people who will be telling you that they know what is going to happen and what this new candidate, Éric Zemmour from the far right, is going to have as a score are just telling you lies. They know that, or they don't know. They are telling you false things, but they are.
Which is probably worse. Yeah.
Nobody knows what's going to happen because it never happened. So you cannot really draw on any past experience, or it's hard. You have to have a hierarchical model with priors that are chosen very carefully. And so anybody that tells you with certainty what's going to happen is just telling you his opinion.
Yeah. I think the biggest difficulty with French, if I need to summarize, the biggest difficulty with the French elections is that you need a lot of expert knowledge to, like, you can have a fancy model, but that model wouldn't be anything with that expert knowledge.
But the expert
and
knowledge,
I guess we're lucky to have the expert knowledge, and
but the expert knowledge on its own, it's not sufficient either.
Yeah, so so you've got both, so that's great. And so what do you think? So the model that you're working on Postposition is it's basically a prediction model, like 538 did. And I think it would be interesting for the listeners to go back and explain exactly what does it mean when we say that we predict the result of the election, let's say 6 months from now, 2 months from now, and when really is it close to, when can you assume that it's going to be close to the actual result? So what does it mean to say that we forecast?
So the further you are from the election, the more the model is relying on the historical forecast. So it's basically saying, okay, in the absence of any data, I'm going to assume that what's going to happen is going to be pretty much similar to what already happened in the past. So if the election is not completely different from history, you can get a pretty decent forecast just already based on that. The model we have already here in production, I ran it like 3 to 1 month before the elections of 2017. And already 3 months before the elections, you could have a decent prediction of what would happen, which is encouraging because the 2017 elections were kind of peculiar because the center party, which is Emmanuel Macron's party, which was a completely new party, but still you could put that in the bucket of the center party.
In the center, yeah.
Like the model was already very good at predicting what its results would be 3 months before the election, although with, of course, a lot of uncertainty. So that's what we mean when we predict the election results. It's like the further you are, the more it relies on historical data. And the further and the closest you are to election day, then the more important polls become. And the model has less time to revert to the historical mean.
I mean, just for the listeners who are not familiar with this kind of model, what do you mean with similar to what we saw in historical data? Like, how do you pull this history in your model? Like, how do you include that history in your model? Because I think everyone can understand how you aggregate polls together to get a trend line. Everyone does that. But how do you include this historical information in your model?
Yeah, so it's basically a huge correlation machine. So we have all the results from past elections, and we have a structure in the model which relates each elections to each other. And then the model sees all that data, and then its job is to estimate the timeline of the election and do a backwards walk from election day to where we are right now. So for instance, 3 months before the election, and try to infer what that timeline will look like. And the way it can do that is we have the results of past elections and we have all the polls from past elections. So we can learn from that, and we do it. And also the way we pass that information from an election to another is, as I was saying, each timeline is modeled by a Gaussian process, but each election and each party has its own Gaussian process. But each of these election is then pulled to a higher level Gaussian process for each party. And that means that basically the model is saying each party kind of has its inherent timeline, no matter the election. Like parties some parties tend to be very stable. Like the far right party, for instance, its support is usually very stable. The right party, really stable too. Whereas the left party, the center party, the far left party, they tend to be much more versatile, and their support can change much faster during the election than the other parties. So the model needs to know that and to learn that, so that in the new election, where we just have the new polls and we don't know how the timeline is going to look, then when it does prediction, it's able to say, okay, so that party historically has been pretty stable, and yeah, so I think it's going to stay stable until that date. But that party has been not very unstable, and so I need a bigger standard deviation on that prediction, basically.
Yeah, and I guess the thing that it took me a while to understand was the way you can predict the result is because elections is this idea, I think Gelman talks a lot about it, is that the result of the elections is actually very predictable. And I don't think he's the only one to say that, but it's very predictable from fundamental data like unemployment,
it's
GDP growth or anything like that. And so you use that model, you model that and the score of each party depending on these variables. And then knowing these variables at this point in time, you can just make that forecast for the election. And there's this idea that the opinions, the intentions, the voting intentions might be different today, but it's just because the opinion is taking a long time to reach. I like this idea that the opinion just like, just doing its random walk, but just like, just going towards where it was supposed to be.
Yeah. It's like the idea is as I was saying, candidates don't matter that much. Elections matter, but I see them as just an offset from a latent reality. Like imagine there is like just just like a latent, support for each party that exists in the matrix. And so for each election, which is a given timeline, so 3 months of election campaign, you can already do that no matter the election. You can already say, usually the left party behaves that way, the green party behaves that way, and so on. So you can already do that. It's like a latent, non-existent in the matrix, just that as a baseline timeline. And then you add an offset, which is related to the election. Like when that happens in the world, then it's an offset. It's a realization of that object. And it's like you have the class, the Python class, but then you have the Python, the object of that class is the election. And it's just a variation around that baseline, around that class, but it's still that class.
Say you have 1 minute with every one of you, so I'm going to time it. You have 1 minute with a random Twitter follower of your account. How do you explain to them?
Yeah. So that depends what they ask me at the question, actually. But I won't enter into those levels of detail and so on. Some people do ask, but what does far left mean? And then I enter into the details we talked about, which are, I know you think that parties are very important, but it's not something I see in the data. Basically, like parties are actually quite stable, and you can have like an idea of what a far left party is, no matter what the name of the party and the identity of the candidate. That's why I would say. But yeah, basically, I almost never enter in the details of the model unless prompted. I focus on the results.
And what if people say, "Oh, all the models are wrong"?
Yeah, well then you say it's true. But look at the alternative.
But how do you convince them that it's useful? That's the question. People are just, have seen many models that were very, very wrong about many things. I mean, thinking of COVID, for instance, some models were made public were just, obviously wrong. Some, I'm going to answer the question, but how would you go about someone telling you this? Like your model is useless. All models are wrong. Therefore, your model is useless.
Yeah, I try to dig into the motivation of that person, because it's a very nihilistic thing to say. And then I would try to understand why he's saying that or she's saying that. Because, that's true, all models are wrong. But what's a model? Like, because what's the alternative? Okay, is the alternative just everybody says what he wants and what he thinks, and we all put everything on the same level, at the same level, and everybody is right, and there is no hierarchy in how you came up to that way of thinking, because like then everything is wrong and everything is relative basically, and there is no hierarchy between someone who came to an opinion that was through a method, so a scientific method that's been tested for centuries now, and that shit works. That's how we fly. That's how we can come up with vaccines, and that's how we die less. And somebody who just like thinks, like lets basically his mouth say anything that his brain comes up thinking that each one of his ideas are great. So that would be that. First, look at the alternative. Is that the alternative you want? And second, what the opinions in your head are a model. Like they are a simplification of the world. Nobody sees the world exactly as it is. And so what you're telling me without a quantitative model is already a model. It's just a model with just priors. And your priors are very bad because they are not even explicit. So everybody has a model, but our model at least is explicitly on GitHub. And also we can update it with the data because we put that on the computer.
I think, that was an answer to someone who was like, oh, these guys are not serious, blah, 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 blah. Don't follow them. And we're like, well, you know what? People can just look at the code and the math of the model and just make their own opinion.
Yeah.
That's the good thing is, probably.
But the point is, that everybody has a model in his head. It's just that it's not the reality that you have in your head. It's a prior structure, but you haven't explicited it. And you are not able to update it because we are all biased individually, and we don't want to update our priors when the posterior would say that we were wrong or that it's an idea that we don't like. And also, it's very hard to do that for our brain. Like, we're very bad at math, basically, and computing, and we should just, the computer is better at updating that prior than us with the data.
Yeah, so all that to say that, Bayesian statistics in the real world is the wild is complicated. I guess modeling is complicated in general, especially in politics where people get pretty worked up very quickly about basically anything. You'll always find someone who will threaten to kill you for whatever reason. Because you're not rooting for their candidate.
Yeah, it's something that I often remind people, this is hard shit. It's just it's super hard. And kind of nobody knows what he's doing, but you try to do something. Yeah. And when did
you see a difference? Did it change the perception of people or not that you've interacted with, between 2017 and 2022?
Yeah.
Are more people more receptive, or on the contrary, more have more doubts?
Yeah, no. I find people at least much more curious about statistical modeling than in 2017. In 2017, there were only two of us doing that, and we were the weirdos on the block, and people didn't really understand why we're doing that because it's super easy to forecast elections or stuff like that, or just people didn't understand why quantitatively modeling something is important. Now, people are much more receptive, I think, for at least two reasons. Just the sense of history. Data science is much more prevalent everywhere now, including in newspapers, newsrooms. In newspaper newsrooms. So people are more exposed just to data and models, and they have these phones in their pockets, which are supercomputers, basically, and data is everywhere and statistics are everywhere. And the second reason is COVID. COVID was awesome for us.
Okay, interesting.
Yeah. COVID was awesome for us because it exposed people to complex data, to testing, which is perfect for Bayesian stats, right?
It was real world epidemiology.
Yeah, I talked about that with David Spiegelhalter in episode 50.
Yeah, wrote a book about this.
Yeah, and that
very interesting book.
That was awesome because it exposed people to modeling and the fact that modeling is incredibly hard. But it's because the world is incredibly complicated and there is no easy answer. And just putting your head in the wind, in French, we have that expression, you just the wet thumb and then you just have the direction of the wind, and then you just say that. It's not good. It's not what you want.
If you wild guess, yes.
Exactly. Yeah. And in a way, the pandemic was a great way to put that in check. Like the countries who first did completely stupid stuff were hit incredibly hard. And then we all started to understand that we need the scientific method to get rid of that virus. So that helped us a lot, I have to say.
I mean, and we got the opposite as well. I guess what I see so it's more true among the more educated people, but people who don't have a massive background in science is the most skeptical approach to science. Actually, I've seen many people who were, epidemiologists were completely wrong and science is bullshit. And it's like, well, first of all, yes. Yes, in the sense, almost every science that makes a prediction that is not physics, or, that is not something that makes predictions about something very simple, like physical phenomena. I say that as a physicist. It's very simple. Like, we'll make mistakes. I find that you have this double tendency of like, people who've never really been exposed to models now are like, oh, wow, people can do that and it's not that bad. And then you have people who were vaguely familiar but expected perfection, modelers and from science, but who are like rediscovering the truth about science, because it's something that, if you look at philosophy of science, it's not a new idea. Is that we're screwed because the world is very complicated.
Yeah, but it's exactly that. Like, the tolerance for failure we have towards computer is extremely low compared to the tolerance for failure we have for humans. It's just like, and you can see that in automated planes or cars. It's like people expect absolutely no accident from that. Well, no, it's like the huge expectations. They think that poles are perfect. Well, no. But again, look at the alternative. It's not as if humans were perfect drivers. And even if computers have less accidents than human drivers, well, then maybe it's interesting to look into that. So what I find super interesting now is that this is at least something we discuss more, and that people have in mind, that the human brain is an amazing machine, but it has its own weaknesses, especially when it comes to decision-making under uncertainty, and that we probably need to be helped with that.
That's pretty cool. So it's true that today people seem to be more interested into this modeling stuff thanks to COVID. And so what are you particularly excited about this project for this year? Like, what is your dream scenario? What do you hope to be able to do is a better question, better way to phrase it, I guess.
Of course, for Postposition, I hope the model will be good. And the best scenario would be that poles are off in some way that the model can anticipate, and the model will not be lured by those polling errors. That'd be the best, because then they will show that would show people that even better would be that the poles are off in a way that favors novelty, because that will be super appealing to people because we love novelty, And so what would be awesome is that the poles overestimate Zemmour, for instance, so the second far-right candidate. And so that way, like, people will be like, oh my God, is he gonna be at the second round, and so on. But in any case, I think it's going to be very close. Like, the results are going to be very close. And so you need uncertainty estimation, and also you need past elections and history to guide you here, and good priors. And people here basically don't have priors. They are all behaving, like frequentist, like completely flat priors, and they just look at the data and the polls.
And that would be pretty cool.
Yeah, that'd be awesome, because then the model, it would be more conservative. And so it would be lured much less by the current data and the bias in the polls. And it would be able to have kind of a contrarian view of saying, people, like, just calm down. Usually history tends to repeat itself. And so keep in mind the uncertainties and so on, and kind of everything can happen. Or this scenario is still is a plausible scenario, but not that much. And that would be the best, because then that would show to people the benefit of modeling, the benefit of drawing from history and from prior knowledge, and that polls are not perfect and they are noisy.
And also, listeners have to know that French people love to hate polls. So that would be also, that's a very French answer as well. It's just say, I hope that polls are wrong.
Yeah, exactly.
And they will be wrong. They're always wrong.
Exactly. Because then
it's a tragedy of being pollsters is that you are always wrong.
Exactly.
It's fine as long as they're wrong in different ways.
Yeah.
Okay, so that was very interesting, but we're going to have to wrap up. I'm going to let you go about your life. And I'm going to ask you 2 questions I ask every guest at the end of my show.
That's awesome. I didn't know about that, but that's a cool idea. Well done.
Okay.
Yeah.
If you had unlimited time and resources, which problem would you try to solve?
Damn, it's a hard one.
I know.
Yeah.
When you've never thought about it, it's a very hard one.
No, very original question too, I have to say. Yeah, so that one, of course, super hard, but that would be education to the scientific method. I think we talked about that already here.
Okay.
You can see it's something.
How? At what scale? How would you go about that? What do you think is the biggest, what are the low-hanging fruits?
Yeah. So I think the lowest hanging fruit is making people less intimidated by science and math and physics. And the way to do that is to, can you say narrate? And I think a good way to do that is to narrate the history of science. To remind people that science is not something dry. It's not equations. It's people who came up with those equations with huge struggles with themselves first, because of course scientists have egos and they wanted to be recognized and not be forgotten, and there were struggles between them. And that's a great thing that Aubrey Clayton does in his book, is to put back the context and the socio-political context of frequentist statistics and Bayesian statistics at the time. And also because these people have have interesting lives. And explaining how Einstein came up with relativity, and that he was working as a public servant in Bern at the Bureau of, I don't know the word in English.
Patents.
Yeah, patents. Sir, thanks. The Bureau of Patents, and he came up with those ideas, and that's amazing. And the life of Newton, the life of all those scientists who contributed these equations that we know today and that we use and that help us in our lives, but helping people understand that it's not uncommon for science to have struggles and ego struggles and to make mistakes, as we're seeing right now. With COVID, we saw basically science in the making. That was research that we saw. So research is very messy, but then after research is gone, you have science. Science is the scientific knowledge that we got through research. But to get to that, you have to go through a process of enormous struggles and self-doubts and fights between people. And I think it's a way to make people more interested, because you relate basically to the life of someone. You don't relate to an equation. You relate to someone who struggled to get to that equation. And I think that's a good way to do that.
So that would be for a new podcast, Learning Scientific Method.
I honestly, if I had unlimited time and resources, that probably would be a second podcast I would make, telling the life of scientists. I
would definitely listen to that.
Yeah, me too.
And then the second question, if you could have dinner with any great scientific mind that is dead, alive, or fictional, who would it be? I think I know the answer, but tell me.
That's a good question. Yeah, so that one is super hard. The first one I answered that question was in episode 0, and I said Condorcet, so I'm going to change now. Although I'm still going to pick someone from the kind of the same time. That would be Pierre-Simon Laplace. So French mathematician, genius mathematician, and I think he did some physics also, right?
He did. He did.
Yeah. He was a genius.
At the time they knew everything.
Yeah. So, and he is basically the father of Bayesian stats. He really understood. So first he rediscovered Bayes' theorem on his own, was very disappointed when D'Alembert, so his mentor, told him, that stuff actually was already discovered apparently. So he was actually very depressed to learn that. It's incredible to think that Laplace would be depressed, But then he wasn't depressed for long because he understood the implications of that formula and developed all Bayesian, the framework, the whole framework of Bayesian stats. So I think that would be super interesting to have dinner with him. And also he had an interesting life. He didn't come from privileged background. He came from a poor family from somewhere in France in the countryside and was just incredibly good at math and had the chance to go to school. And there his math teacher was impressed by him and talked about him to people in Paris. And he got a grant to go to Paris. And that's where D'Alembert, who was like a superstar at the time, took him under his mentorship. And so yeah, that's must be an interesting life. I'd like to learn more about him.
Cool. All right. Well, Alex, thank you for coming on my show.
Thank you for inviting me.
Yeah, as usual, I put the links in the show notes. Very interesting stuff, Postposition, the open source work, etc. And well, thank you again for coming. And
thank you
talk
again.
To you soon.
Yeah, thank you again for inviting me. And I'll be glad to be back on the show anytime.
This has been another episode of Learning Bayesian Statistics. Be sure to rate, review, and subscribe to the show on your favorite podcatcher or on Podchaser, and visit learnbayesstats.com for more resources based on today's topics, as well as access to more episodes that will help you reach true Bayesian state of mind. That's learnbayesstats.com. Our theme music is Good Bayesian by Baba Brinkman, with MC Lars and Megaran. Check out his awesome work at bababrinkman.com. I'm your host, Alex Andorra. You can follow me on Twitter at Alex_Andorra, like the country. You can support the show and unlock exclusive benefits by visiting patreon.com/learnbayesstats. Thanks so much for listening and for your support. You're truly a
good Bayesian. Change your predictions after taking information in. And if you're thinking I'll be less than amazing, let's adjust those expectations. Let me show you how to be a good Bayesian. Change calculations after taking fresh data in. Those predictions that your brain is making, let's get them on a solid foundation.